Hello mates, in the previous video we just defined the two coordinates that we are going to use in the vertical system. We are going to use the x, or let me say the x coordinate is going to be called the azimuth. It is this angle here from the O, or the origin point, to where the vertical circle cuts the horizon. That point, this angle here, OCM, is going to be our azimuth. And then the elevation above the horizon or below the horizon is going to be our MCS, that pinpoints the star. So this OCM just tells us what vertical circle it lies on, and then this MCS tells us the particular point on that vertical circle where the star is. So these are the two coordinates that we are going to use. What I didn't state was OCM is measured from 0 degrees to 360 degrees through east. It's from 0 degrees to 360 because it's all right around the horizon. And then the MCS is measured either from 0 degrees to 90 degrees, either above the horizon or below the horizon. So it's going to be from 0 degrees, you can say it's 90 degrees, and it's going to be above or below the horizon. And it is known as the what? As the altitude. So this vertical system is also called the altitude azimuth system, for obvious reasons, because the coordinates are the altitude and the azimuth. So now let's just get a few examples. Let's just do a few examples. Can you see the azimuth of the zenith? Let me start with the poles. At least if you start with the poles, maybe you'll be in a position to understand. But let me erase this page, because I want to write it on a page that is a diagram for easy explanations. So bear with me as I do some deletion here. If it was a computer, I would just highlight this stuff and delete, but we are going old school. So, but this system, as we are going to discuss, you will see why this system is not very, very effective. We are going to see why this system is not an effective system compared to the other systems that the astronomers later developed. And that is why we have so many systems. It's because some of the systems, they fail, and we are going to see the failure of each system and why they had to develop a new system. All right, I think I'm done now. Yeah. So now let's see. Now we are just going to explain a few things. Let's look at the south point. The south point, we are going to discuss the azimuth of the south point and the altitude. These are just examples. So now the azimuth of the south point. The south point, if the person is in the northern hemisphere, what is the azimuth of the south point? We are going to discuss it from a point of view of someone who is in the northern hemisphere. If someone is in the northern hemisphere, this is their origin. So their origin is here and their south point is there. So can you see, to measure the angle, it will be 180 degrees, because now our OCM, our M, will come here where the south point is, and then our OCM will just be measuring the straight line angle. So for this person who is in the northern hemisphere, it's going to be 180 degrees. If the person is in the southern hemisphere, then the origin is at the south point, so the azimuth will be 0 degrees if the person is in the southern hemisphere. But for this person who is in the northern hemisphere, it's 180 degrees. In the altitude, it is the measure of angle above the horizon. But can you see, the south point is actually defined as where the celestial meridian cuts the horizon. So which means it's an intersection between celestial meridian and horizon. Intersection basically means this south point also lies on the horizon. So the altitude will be 0 degrees. Then the east point. The east point for this person, the east point for this person, the east point is, we measure azimuth in the easterly direction. So this east point is at 90 degrees. And then since it's a point on the horizon, it's always a point on the horizon, the east, west, north, south, they're always on the horizon. So this one will be 0 degrees altitude because they are points on the horizon. And then the north point, depending on where the person is, this person is in the northern hemisphere. So his north point is here, and it's coinciding with what with the origin. So this one will be 0 degrees, and then his altitude will be 0 degrees. Then the west point is 270 degrees, and the altitude is 0 degrees. Then the zenith, let's look at the zenith. The azimuth, we cannot measure the azimuth of the zenith. Why can't we measure the azimuth? Because azimuth measures the point M. But this point M was created because of this star. I can also create another point M. If I'm to measure for zenith, I can create a point M like this, and it will be here. Or another one, it may be this. It's still passing through Z. Or another one. Or so infinitely many M's that I can create that pass, or many vertical circles that pass through Z. Because for you to measure the azimuth, you have to make a great circle, a vertical circle that passes through the point. Here the point is now the zenith. So there are infinitely many vertical circles I can create that pass through the zenith. And they will give me infinitely many M's. So the azimuth for the zenith is undefined. But its altitude is plus 90 degrees, as is obvious, isn't it? And then the nadir, because it's 90 degrees, because obviously it will be 90 degrees above the world. No matter where the person is, the zenith is always on top or above the what? Is always above the observer. So it's always on top. And whether it's going to be the southern hemisphere or the northern hemisphere, the zenith is fixed with the observer. It's above the observer every time. So the altitude above the observer's horizon will always be plus 90. The nadir, same applies for the nadir. I cannot define one vertical circle that I can use as the M. I cannot define one. So which means the azimuth is undefined, and the nadir is minus 90 degrees altitude. So this was just I think these can serve as examples of how to find these. They are part of what? Of how to find these. And notice something: the altitudes of objects that are below the horizon are given negative values, and the altitudes of objects above the horizon are given positive values by convention. But I said this system is not very useful. It is because it varies with time in a very complicated way, and also this system, for a person seeing this star in the northern hemisphere, this system is different because it depends on the person's horizon. Anything that depends on the person's horizon is obviously going to be different when the person moves places, because the horizons will be different. The horizon is different when you're in USA, and it's different when you're in Mexico, because the horizon follows the observer. So this star here will be measured by different vertical circles that cut the horizons differently, because since there are going to be different horizons, it means the M here, the M will be different. And also the vertical circles are defined by what? By the person's zenith. People's zeniths are different depending on where you are. So which means this star will have a different azimuth value, and we have a different altitude value, and these values will depend on where the person is. That is not a good system, because I cannot use a system that applies in the USA only and try to use it in South Africa. We need a universal system, just like universal law of gravitation. We cannot have a system that applies in the USA and say, okay, no, these coordinates that we have given only apply when you're at WITS. When you go to UJ, they do not apply. So so it becomes very, very difficult for us to pinpoint stars. For me to call a friend at UJ and say, okay, look up to star S But my coordinates here at Wits are 180 and 0 degrees. I do not know about the coordinates at that point. The person will not be able to find the star because the horizons are different. I hope I've explained that well. That is the main lack of this system. That's why it mainly lacks. So in the next video we are going to discuss a better system that no, I think before we do that, let's actually discuss a very important part of this system. Though with its lack, there's going to be an interesting part with this system. Imagine this is Earth, right? Imagine this is Earth, and this is going to be the Earth's equator. This is going to be the Earth's equator. Imagine that this is the Earth's equator. This is going to be the Earth's core. And imagine the observer is here, which means their zenith or plumb line is going to be like this, isn't it? And now, if observer, okay, not like it's like this. Imagine that is just Earth, and this one was the what? North geographical pole, which means the North Pole. The North Celestial Pole is somewhere here, and I'm just going to write P for Polaris, the star called Polaris. So imagine that is the star Polaris, and this one is the South Geographical Pole. So here is going to be our South Celestial Pole, and let me just write the North Celestial Pole up here. So this is our equator. So now, with the same situation, this is going to be our equator. And up there is going to be our celestial pole called Polaris. That's where the star is, right up there with the celestial sphere. Now imagine this person is at this point A. If the person is at this point A, can you see, probably they are facing this side, they are facing up like this. This is what their orientation, their orientation will be like that. So their horizon will be like this. That is going to be their horizon. And this is going to be their axis. Their axis is going to be like this: the zenith up there and the nadir down there. But we are not going to draw those. We are just going to draw the. We are just going to draw the horizon. We are just going to draw the horizon. When you draw the horizon, this person is in the northern hemisphere, so they are going to see Polaris here. So their visible star is going to be somewhere up there. It's going to be somewhere up there. So now let's put an angle here. We are going to call this angle phi, and as you can see, the angle phi is the person's latitude, because it is the elevation of the point where they are above the equator. That is the definition of what? Of latitude, if you remember well from the terrestrial coordinate system. That phi is the angle of elevation above the geographical equator. Since this is the geographical equator phi, we are measuring the elevation above the geographical equator of point A. So phi is called what? The geographical latitude. That is the person's latitude. So let's just send down a line here to create a right angle triangle here, and let's call this point M. Let's call this point M, and let's extend this line going all the way up to infinity, or to the celestial sphere. So the observer is at A. Let P be the visible pole. This is the visible pole. So now we are going to draw a line AP1, which is parallel to CP. This is going to be our C, as mentioned here. This is going to be our C. So this line here, AP1, we are just going to call AP prime like this. It's obviously parallel to what? To CP. So we drew that. Since the radius of the celestial sphere is exceedingly large, we say these points are going to be up there in the celestial sphere, but the celestial sphere radius is so large because it has to include all the astronomical objects. So it's very, very large. Since it's very large, P and P prime, for all practical purposes, coincide at the celestial pole. So we can just assume that this P is going to point at the same point as this pole, because the radius is so large, it's so far away that the separation of these two is so insignificant. So hence, now we are going to have our horizon H. We're going to have our horizon H. Now, can you see something? Let me see if I can best draw what I want you to, or what I want you guys to see. So can you see angle H? Let's consider angle HAP. Angle HAP. Our angle HAP, this one here. By geometry, this angle HAP is equal to phi. It's equal to phi. We can look at what is happening there. What is happening there is basically something like this. It is this line here. We have a point C, and we have our point A, and we have our horizon like this. We have our horizon like that. So this one is going to be H, and we are going to have our line P prime, and which is going to go down to M. And here is what is our angle phi. So this is 90 degrees, right? So this angle here is going to be 90 minus phi. It's going to be 90 minus phi. But can you see these lines? They are like this. So this angle here is also 90 minus. It's also 90 minus phi, isn't it? It's also 90 minus phi. So since that is also 90 minus phi, what we need to realize is this is the observer, right? This is the horizon. This axis here was leading to their zenith, as I said. So which means this angle here is 90 degrees, because this is the horizon and this is the line for the zenith. The horizon and the zenith, they make 90 degrees. So this angle here is going to be 90. The full angle here, because the here is the zenith. So the full angle here is going to be 90, because this is the horizon, this is zenith. So we need to calculate this angle here. And we know that this full angle is 90 and this small angle is 90 minus phi. So we just do 90 minus phi to get the remaining, this one here. So to get this remaining is just 90 minus phi. 90 minus 90 is 0. Minus phi and minus phi is just going to be phi. So our angle here is basically phi. That's why we said our angle HAP prime is equal to phi, which is what? The altitude. As you can see, it's the altitude. But we said P prime is going to coincide with this pole star Polaris, which means for someone here to see this star, they just have to raise their head along P prime. But you see, when they are raising their head from the horizon, they are raising their head through an angle phi. But phi, what is phi? Phi, we have defined phi as the latitude. So basically, the altitude of visible pole, or how they are going to raise their head up, to see that Polaris star, since these two are coinciding, how they are going to raise their head up above the horizon is equal to phi. But phi has been defined as the what? As the latitude of the observer, because that is the elevation of this point above the celestial equator, as you can see. So looking at the Earth, this is equal to latitude of observer. Latitude. So this is a very important point, that the altitude of the visible pole is equal to the latitude of the observer. So if the observer is 20 degrees north, then they are going to see their visible pole is the north pole, because of the northern hemisphere, and at 20 degrees above their horizon. That's basically what it means. So if the person is at 20 degrees south, they are going to see the south celestial pole, because of the fact that they are in the what? In the southern hemisphere. But at what elevation above their horizon, they are going to raise their head 27 degrees. So that is very important. That is a very important part about this system. So we are done with the vertical system. I hope you understand. And in the next video, we are going to start our first equatorial system. Let me show you our game plan. Our game plan now says we are done with this. We now need to move to the first equatorial system. When you go to the first equatorial system, then we'll see how to measure the angles, and we'll do the same for the second and then the ecliptic. So for now, let's just stop the video here and prepare for the first equatorial system.